Well, very warm welcome to you all this evening. It's always a great pleasure to attend and welcome people to these inaugural lectures. My name is Rachel Barron, for those of you who don't know me, and I'm the Dean of the Faculty of Natural, Mathematical and Engineering Sciences. It is particularly delightful to spend time in the company of people from the Department of Physics. Physics is you know, it's an amazing discipline, isn't it? It's this combination of observations, developing theories, testing them, and it's done by super smart people who are fascinated in pushing forwards the boundaries of knowledge. So I'm really looking forward to this evening. And we've got two professors who you know well, and they represent a real breadth of physics, capturing the more computational side and experimental side. So I'm going to briefly give a little bit of an introduction to them. So first up, we're going to have George Booth. He joined King's in 2014, first as a Royal Society URF. So he joined us from Cambridge, where he'd been a fixed-term lecturer, a JRF at Trinity, where he completed his PhD. Although in the chemistry department, which is a nice touch because we're very interdisciplinary here at King's, so very nice to hear that connection there. Also having spent time at Princeton University before joining us. Now, George's interests lie primarily in computational electronic structure theory, particular focus on novel techniques that push the state of the art in both classical and quantum algorithm development. As I mentioned, background in both chemistry and physics. His particular interest is the development of scalable approaches for extended systems, working at the intersection of traditional quantum chemistry and also numerical physics approaches. So that's George. And after George, we'll have Jeanne Wilson. She's also a professor here in physics, professor in particle physics, and an established researcher in the field of experimental neutrino physics. She studied at the University of Sheffield, where she had an MPhil in physics and astronomy, and then did her PhD at the University of Oxford at the Sudbury Neutrino Observatory, producing the first energy spectrum of 8B solar neutrinos. Before joining us, she had a postdoc fellowship at the University of Sussex, working on the COBRA experiment, and then a Leverhulme Early Career Fellowship at the University of Oxford on the SNO Plus experiment, both in the field of neutrino-less double beta decay. From 2010 to 19, she was senior lecturer and then reader at Queen Mary University of London, where she worked on the T2K, the SNO Plus, and the Hyper Kamiokande neutrino experiments, which I think I saw some pictures at Open Day on Saturday, which looked very cool. These are the sticking things in mountains, isn't it? Which we'll hear more technical descriptions soon. She joined King's in 2019 to help establish the new experimental particle physics group, bringing her research on SNO plus 2K and Hyper K. So that's the kind of formal part introducing you, but I quite like trying to think what connections and what I know about these people. So the last inaugural lecture we had Chris Lorenz and John Alexander, and the common theme there was beer. I think that was the common theme. Now for Jeanne and George, what immediately jumped out to me, perhaps not quite so comical, a little bit more of a serious theme actually, was their work in equality, diversity and inclusion. As you probably know, Jeanne played a real lead in the physics submission of a successful second Athena Swan Silver Award, and with a really concrete and impactful action plan, we've really seen increases in the number of percentage of female students and academic staff in the department in recent years, which has a real tribute to the hard work of many people, including Jeanne. For George, as I say, there was a common theme here because when I first arrived at King, or shortly afterwards, George was popping up occasionally because he was on paternity leave. And I think this is a good reflection of how some of the work that's been done on improving gender equality has had a really positive impact on all staff. And speaking very personally here, I certainly would have had a very different experience in my career both raising a family and working as an academic without the very strong support of my partner, and we've had various trading off of career breaks and so forth. So I think that kind of theme is both of you play real leading roles and models for those people following you in your footsteps. So thank you for that too. But I've said plenty enough. You're here for the main event, so we'll start with George and then Jeanne. Thank you very much.
Thank you, Rachel. Hi, thank you very much for all being here. So back in 1960, there was this very influential article written by Eugene Wigner that I bastardized for my title. He said, "The unreasonable effectiveness of maths in the natural sciences." And I bastardized this to say, the unreasonable effectiveness of computers in the quantum sciences. So hopefully that gives you a little bit of the spirit of the sort of research area I'm in. I try and develop numerical and computational approaches to quantum many-body problems. So I'm going to try and give you a little bit of feeling for the sort of creativity and the excitement that I have for this field, why I find it so interesting, and a few little personal reflections and a couple of confessions as well. So what do I mean by quantum many-body problems? Sounds very esoteric and abstract. I'm not thinking about particles in the center of black holes or exploding galaxies or anything exciting like that. My kind of application domain is much more prosaic. It's the world around us, and I try and keep really quite a broad application domain across things like quantum chemistry, small molecules reacting. We have theoretical spectroscopy, the action and reactivity of biomolecules. We have kind of the idea of kind of emergent magnetic order and quantum phase transitions in paradigmatic lattice models, and how those kind of spins interact with each other, all the way through to kind of material science problems, where we're thinking about realistic materials from a first principles perspective. Now, I try and make sure that we really cover this whole gamut of applications, and really what I should have done in this talk is talk about some of these applications, something that you can hang on to, something tangible and real. But no, I've tried to make life more difficult for myself and really try and talk to you a little bit about the dark art of how to develop numerical approximations and computational methods, which then go into calculating some of these quantities. And that's really the thing that keeps me up at night, along with my 2-year-old son. But the first thing to say is that this really shouldn't even be possible. It was known from very early in quantum mechanics just quite how formidable this challenge was. And Dirac, nearly 100 years ago at the inception of quantum mechanics, kind of summed it up. He said, essentially, the fundamental laws necessary for describing the whole of chemistry and basically all of physics were already known. It's just that the equations are too difficult to solve. And this famous quote, it wasn't really put into the context of complexity of computer science terms at that time, but really what he's talking about is explosions of sort of exponential complexity in these equations. Now, I take very much the approach taken by David Mermin when he said sort of shut up and calculate when people started talking about quantum mechanics. I should say that actually this wasn't a direct response to Dirac. I just want to make that clear. So where does this problem really arise? Well, people start talking about quantum many-body problems as having exponential walls and cursors of dimensionality. And it can be summed up in this way, in that the central quantum variable is the wave function. That wave function is a function of every single particle that you want to describe. So if you have a fixed resolution for each variable and you add another variable, then it needs to depend on all of the other variables that are already there. And then you can see that as you add more variables, the number of degrees of freedom that you have to contend with kind of blows up exponentially. But once you have this object, you can get all observables that you might be interested, that you want to predict. And the unreasonable effectiveness is from this exponential complexity, we can actually get predictive approximations that really allow us to make real progress. So, you know, we have these problems, though, that we have to overcome. We have kind of exponential storage of this wave function object. We have exponential compute power that we need to integrate over all the variables and calculate these observables, these expectation values that we're interested in. Then there are more technical problems to do with orthogonality catastrophes, people that want to bash the field. Most famously, Walter Kohn, in his Nobel address of 1998, said that actually wave functions weren't even valid numerical approximations to work with, because the overlap of any approximate wave function with the true wave function decreases itself exponentially with system size. So to burnish my credentials as a new professor of theoretical physics, we can do some kind of back-of-the-envelope calculations, and we find indeed that the overlap of any approximate wave function with the true wave function decreases exponentially with system size. But on that same back-of-the-envelope, you can show that actually the quality of the expectation values, the observables that you're interested in, with respect to those approximations, they don't decrease exponentially. So we can find that approximate wave functions can nevertheless provide meaningful expectation values. So we can rule that one out, but we still have these other problems: exponential storage and exponential compute to be able to make any kind of progress. And how quickly does exponential really matter? Surely we can still make some kind of progress. Well, this is a very recent publication from my group that we're very proud of. This is looking at a very, very, very simple chemical reaction between two water molecules. And there are only 20 electrons, 20 quantum mechanical particles that we're worrying about here, but we had to really introduce brand new approximations. Brute force methods were completely impossible for this sort of size system. So really it kicks in straight away. You already need to be creative just for the simplest systems that you might want to start with. But why on earth am I interested in small chemical reactions between two small molecules? Well, actually, Rachel gave the game away somewhat already in that, and this is slightly awkward in an inaugural lecture for a theoretical physicist, is that I'm not really a theoretical physicist. And to explain this a little bit, we have to go back and do the obligatory world map of all the exciting places around the world that people do inaugural lectures for, showing all the exciting places that they've done research. This isn't going to be nearly as impressive as Jeanne's, I presume, but I haven't really done research in very many places. So the world map is really, really redundant in this case, and so we'll just zoom in on the UK. I was a reductionist at heart, even at school. I kind of wanted to find out what was at the bottom. And so originally in my undergraduate, I was seduced by an undergraduate program at Nottingham, which was entitled Chemistry and Molecular Physics. And I thought this would be all about quantum theory from the beginning. But in reality, of course, what it was joint honors chemistry and physics degree. And after 2 years of titration, I couldn't take the labs anymore, so I skipped over to plain physics for the last 2 years. But coming out of my master's, knowing still, next to nothing to first approximation, I was still being a reductionist. I then wanted to go into high energy and string theory and keep digging down. But obviously, when I talked to people, they said that my joint honors chemistry physics path wasn't really quite the right one for sort of high energy string theory. But I saw an advert in a chemistry department which had all sorts of esoteric Feynman diagrams, and it talked about path integrals and lots of things I didn't understand, and it kind of rekindled my interest. So I actually went down to the theoretical chemistry department in Cambridge to do my PhD with Ali Alavi. And that's when we started developing approximations and methods to treat sort of molecular systems at the quantum level with first principles. It went successfully. We got a new method. It could do things that other methods couldn't. We got new results, new approximations. So I was lucky enough to go and get a junior research fellowship at Trinity College after that. For many people, this is the sort of pinnacle place that you could possibly hope to do academia in those sort of hallowed grounds. I found it quite intimidating, I've got to be honest. I was quite anxious. I felt overawed by the surroundings a lot of the time. And so that feeling of inadequacy really persisted there. It probably wasn't helped that my fellows photo in the Trinity magazine announcing the new fellows didn't really have me at my most serious. I never really got on board with dining in a bow tie or which way to pass the port, and it was all slightly awkward, especially when after this came out, Sir Professor Lord Martin Rees of Ludlow, President of the Royal Society and Astronomer Royal, came up to me and said the photo made it look as though a bomb had gone off in my face like some roadrunner accident. But anyway, this was me. I wasn't taking myself particularly seriously. Indeed, Tony's already complained that I'm not wearing a tie for this event. But anyway, so I was delighted then to receive an email from a professor that I knew and very much respected over in Princeton, Garnet Chan, asking if I wanted to join him over there. This is a guy that doesn't take himself too seriously. This photo is from he's now at Caltech, his official staff directory webpage of his. So I flew over there and I spent some time there, which scientifically was absolutely fantastic. Introduced lots of different research directions for me and has influenced my research directions to this current day. So after that, I went back to Cambridge to finish the fellowship and with a fixed-term lectureship there as well, before moving down to King's to start a URF and lectureship there, where on my interview panel was Mark Van Schilfgaard, who I'm very delighted is in the audience somewhere, and also David Richards as head of department, which feels eerily familiar as well. So the point of this story is really to say that between leaving my master's in Nottingham and starting my lectureship at King's, I actually never did, in all of those formative years, research-wise, I never actually was in a physics department. I was in chemistry departments. And so this is sort of, why I don't maybe feel like a proper theoretical physicist. And, I think that has a number of benefits. It has downsides as well. My line manager ribs me on a continual basis about being the chemist in the group. But, it also allows me to then, plead ignorance on any particular topic that anyone wants me to talk about, because I can just claim otherwise from my background. But in seriousness, I think it really does mean that I think of it as a bit of a superpower. This interdisciplinarity enabled me to kind of talk to people in different fields, talk two different languages, find commonalities between different fields and try and exploit them. So it's a rich seam of research. And it's a rich seam of research both in the kind of physical systems that we look at. So here's an example, the pin-up child of condensed matter physics, the iron-based superconductors with these squares of iron atoms connected with chalcogens, and the strong quantum fluctuations there, the strong quantum mechanical nature of the electrons are what drives this exotic high-temperature superconductivity. But those same motifs, these squares of iron atoms connected by sulfur atoms, are found as strong spin fluctuations which drive the nitrogen fixation in the active sites of nitrogenase molecules, which are essential for fixing all the nitrogen in the atmosphere for life itself. And it crops up all over the place. So these triangular molybdenum sulfur motifs, when condensed down, give this exotic spin liquid materials. But, actually, biologically, they're exploited exactly for the same properties in the active sites of formate dehydrogenase. We can also think about people that try and span these two disciplines. I couldn't resist putting this up. This is Ken Wilson in a paper from 1990. Ken Wilson, Nobel laureate in physics, inventor of the renormalization group approaches. Ab initio quantum chemistry, a source of ideas for lattice gauge theories. Ab initio quantum chemistry is an emerging computational area that is 50 years ahead of lattice gauge theory. So to all my high-energy friends in the audience, I think we're still at least 15 years ahead. And there are others, right? So Majorana did the first quantum chemical calculations. The chemists Heitler in London developed valence bond theory, which Anderson says is essentially the same as resonating valence bond theory, developed later on to describe superconductivity. So there are lots of areas where these sorts of crossovers make a huge amount of impact. So I wanted to answer at least sort of one kind of scientific question of interest and go back to the original question that was posed or the original assertion by Dirac, that these problems are essentially unsolvable. And what he meant is essentially exponentially scaling. As the problem gets bigger in size, does the amount of computational effort you need to solve those problems also, does the amount of computational effort grow exponentially? And that, in a computer science term, is the kind of the distinction between an efficiently solvable problem and not efficiently solvable. And to do this, you need to, first of all, understand how the computational effort grows with system size. So you want that to be polynomial. And generally, you can find that easily enough. You just set your algorithm running on bigger and bigger systems, and you observe how long it takes to get your answer. But actually, if you want to be able to solve the problem polynomially efficient, you've got to sort of be able to reduce the error or the uncertainty that you have in that number in a way that computational effort also scales polynomially with it, right? You can't just get a number of unknown accuracy. And this is the one that's really difficult to actually prove one way or the other, right? Because you don't know what the right answer is meant to be in advance. So that's why we don't really know very well. So my research field is about developing heuristics meaning that we don't know rigorously what the error should be, but nevertheless ones that are systematically improvable approximations to the problem, meaning there's some giant knob that we can turn. It's going to make the computational effort more, but hopefully we can converge to the exact result. We just don't know exactly the scaling to that exact result. Why can't I prove the scaling? And this is where we come on to my second confession, and this one's a biggie. So in these inaugural lectures, we're told to say a little bit about your domain, your area, what you do, but also make it personal and inspiring. And that means kind of talking about the hardships that you've overcome in order to get where you are today. Now, I'm a white male from a relatively privileged background. I haven't had to face many of the hurdles that others have had to in order to get into this position. But when I think about what the difficulties are and the things I've had to struggle through in order to get where I am today, then there's a clear standout winner, and that's that I'm not very good at maths. This is something that is true way back from my school years. I was never in top sets in maths. I was, quite low down. I was advised not to do further maths. And the times in which I've kind of proven things or derived something rigorously, mathematically in my research are few and far between. Even sort of teaching my 7-year-old now his times tables, I realize I'm not as quick as I should be with some of the 7s, so it's really awkward. And this is all at the same time while I'm still trying to shed that whole chemist thing and kind of, be a proper theoretical physicist. I guess the point I'm trying to make is that, I'm not, I know a bit of maths. I can get through with some things. I have some intuition. I can smell when things are kind of about right, when they look a bit right. And I have big computers backing me up. And I guess the point is that you can get quite a long way with that. But it is awkward to admit, actually, in a theoretical physics inaugural, especially when many in the department feel that actually the first 2 years of an undergraduate in physics should essentially be applied maths. And so I keep quiet and kind of hide in the background and feel like I've been let into a party that I shouldn't be in. Anyway, let's get back to the physics at hand. So this is what we do. We develop heuristics, systematically improvable approximations. How do we do that? What guiding principles are there? What can we exploit? Well, let's go back to the inspiration originally from Eugene Wigner, the unreasonable effectiveness of maths and the natural sciences. And he talks here, it's not brilliantly rendered, but he starts off by talking about a quote from Bertrand Russell, talking about the beauty of maths and how that echoes beauty in the physical world, connecting it to poetry and things like that. Can we use, if we want to develop sort of quantitative numerical approximations, can we use beauty, symmetry, simplicity to guide us? This is essentially, Einstein was a big advocate of beauty in the development of theoretical theories. So density functional theory, some of you will have heard of, is the workhorse in my field. And it started off with some beauty and simplicity, but when you want to make it practical, papers are now littered by huge tables of results across large data sets fitting to ever more parameters. It's definitely true that there's no beauty and simplicity there anymore. My own work, we've started kind of having to be sort of nimble and exploit emerging computational paradigms, disruptive technology. Machine learning is obviously one of those. So, we develop approximations for wave functions that rely on machine learning principles. And papers start springing up that kind of talk about physical wave functions and physical states that look a bit like this. And this is really abstracted away from any kind of physical reality or beauty or symmetry or simplicity. So that, again, is not something we can rely on. I've also been working on sort of recent couple of months, this couple cluster theory. This is the gold standard of quantum chemistry, really some of the best approximations that you can get. That is certainly not pretty, though. We have to write code to derive the equations. Once you've derived the equations, you have to write more code to write the computer program itself that can run and give you the numbers. And you end up with thousands and thousands of lines of computer code that is computer generated and looks like this. So there's often no beauty and symmetry in these problems. I just want to say a little bit. I'm not speaking about individual group members and people I did these work with, because I don't want it to feel like it diminishes the impact that other group members have had if I don't cover everyone. But I do just want to mention one person just because it raises something. And the person that I'm doing this project with is someone that left my group 2.5 years ago. And people should rightly be shouting, "This is outrageous exploitation. What are you doing? This person is not employed by you." They're not even in academia anymore. They work on it in their spare time with me as a hobby in the evenings. It drives my wife a bit batty when on Slack I'm talking with them at 11 o'clock at night. I do make it incredibly clear to them that this is something they should only do if they want to. And I say this on a very regular basis. This was the response last week when I reiterated this. He said, "As always, don't worry, I wouldn't be working on CC code generation at 11 p.m. unless I really wanted to. Pure love of the game." And I thought that was such a nice quote that I wanted to put it into my inaugural, and I'm far too young to give out advice, but if I were to, it would be do research for the love of the game, not because you're in love with the idea of research or anything like that. And I think that's a really nice way to think about it. So we can't use beauty and symmetry and simplicity, but there are various other kind of physical guiding principles that we can use to develop methods. And generally, we kind of take one of these axes and we walk along it, and we kind of use some perturbation theory or variational principles, and we can kind of cook up a whole different zoo, a really creative zoo of different approximations that we can use for different domains of application. And then we can assess the accuracy of the result, and we can ask the question, do we scale exponentially, or do we scale efficiently or polynomially? And the idea is hopefully that we have some kind of slider bar that we can use, and we can tune the computational effort and the accuracy that we get and observe that convergence. And so this is one example here. This is actually the method I worked on in my PhD. And this is what really got me some name recognition in the field. It generated all the buzz that allowed me to later on get my fellowships. And this is actually a linear scale here and a log scale here. It's a straight line in terms of going to larger and larger systems, which means it's an exponentially scaling method. It's not efficient. But that kind of underlines the fact that it was still exciting, it still captured the attention of the community, because whether it's efficient or not, if you can get new numbers that can't be got before, then it's a method of use and practically valuable. But what we have found, and is increasingly found in the literature today, is that there are other methods and other models and other approximations that we can make where we observe polynomial complexity, right? So this is the kind of the project on kind of these machine learning inspired wave functions. On a log-log scale, we get straight lines and the convergence to the exact results for these frustrated magnetic systems. And that is telling us now that we observe empirically that these quantum many-body problems are actually polynomially complex and efficiently solvable in that computer science sense of the word, right? And we can observe this across various different systems. And it's observed in the literature as well. This is the Hubbard model in condensed matter. If we look at some tensor network approximations, again, on a log-log scale, we get straight lines. And then in quantum chemistry, we get straight lines when we're looking at this coupled cluster hierarchy in terms of the computational effort for a particular energy error. And so it does suggest that there's an unreasonable effectiveness of computers in solving quantum many-body problems. From Dirac originally saying that these should be not efficient to solve, exponentially scaling, we find that certain quantum many-body problems, when using the right method, when we use our creativity, and we use efficient approximations with big computers behind us, we can really make progress. And just to finish, I just want to mention one other point that was raised right at the beginning. Can we switch these two things around? Is there an unreasonable effectiveness of quantum in being able to do computational science? And that's the idea that emerging quantum computers, where we have qubits rather than bits as our logical units, are able to try and solve certain problems of computational science and quantum many-body problems. And so one exciting area of the group is also thinking then about how quantum algorithms fit into this slider bar of accuracy versus computational trade-off. Some people in the field even say, oh, we're still in a job for now, just wait until the quantum computers come. I don't agree with this. I think this is very much an opportunity for new heuristics, new algorithms. And there are many technical reasons why I believe this to be the case, but it's certainly an exciting new playground in which we can play around with new approximations. And with that, I'd like to end, but I really want to thank the best bit of the job, which is working with motivated and really bright people that have come through my group or collaborated with over the many years that I've been here at King's, that have loved the game with me. I'm not going to mention them individually. I'd be here a little while, but they've done things that I absolutely wouldn't have been able to do by myself. I take far too much credit for their work, but it's been an absolute honor to work with them on this. I should also say there's one other team member that's not up there as well, which is my wife, Victoria, who, again, has been with me since the beginning of my PhD, survived the long-distance postdocing that was tough, and is the one with the proper job that often sort of goes unnoticed and doesn't get the plaudits that she deserves as well. But you know, while I'm swanning off on these important conferences for several weeks a year, is left often to pick up the pieces. So she deserves a huge amount of credit as well. So thank you very much.
Thank you, George. It's always a real pleasure to listen to you talk so eloquently and enthusiastically about your work. Before I introduce myself, also a thank you to those of you who have come from afar and also those of you who have come from within London but managed the tube strike. For those of you that don't know me, I'm Joe Barcine. I'm head of the Theory and Simulation of Condensed Matter Group. And I should say that I have a confession. I'm the naughty line manager that teases George for being a chemist. However, since you put up a picture of Paul Dirac, a Nobel Prize winner for physics, Paul Dirac started out as an electrical engineer. So, George, you're way ahead of that. And actually, there's quite a lot of examples of that. Ed Witten, who won the Fields Medal for mathematics, started out in political science. Tony Leggett started out as a classicist. And I think actually in many cases, people bring different perspectives by starting out in a different place. And in many cases, that's actually somebody's superpower. So George, being a chemist at the beginning, is your superpower. Okay. So another person I should also mention, which George mentioned, is Mark van Schilfgaard, who's in town for the National Renewable Energy Lab in Colorado. Mark was for many years the head of the Theory and Simulation of Condensed Matter Group, and in fact he hired both myself and George. And in fact, I remember very clearly when George was hired, because David Richards, who was, again, head of department then and has come back, welcome back, David, mentioned about George being wise beyond his years, okay? And that was a very, very astute observation. I think secretly we hoped that as he got a bit older, we might be able to catch up with him a little bit, but the wisdom seems to be outpacing the aging process. I should say that's not the same for all professors, but obviously not at King's. So to try and summarize George's achievements in 5 minutes is a little bit like asking me to summarize Wikipedia in a couple of pages. It's not going to happen. But as we just heard, George is an absolute world leader in the development of quantum algorithms for understanding the many-body properties of materials. And he's a real pioneer in developing quantum Monte Carlo algorithms and variational algorithms, often with very inventive approaches and tricks that he employs. He also works a lot with industry as well, and actually you've seen his recent work. He's pushing into quantum computing. He brings a healthy amount of skepticism sometimes to quantum computing, but you know, these systems have the ability to potentially outperform classical computers, and the question is, can that be unlocked? And George is absolutely at the cutting edge of trying to achieve that. And I've been privileged to work with him, as many people in the audience as well. However, in addition to all of his research efforts, George is also a gifted teacher and mentor. Okay? He's recently set up a brand new course on quantum information and computing at King's for our fourth-year students and MSc students, and they are truly privileged to have George teaching them. This is an absolutely new emerging area. He wrote that course at very rapid speed, and I might sit in that class myself, actually, next semester. He also mentioned his students. If I remember correctly, I think Ollie, who was there, actually even turned down a position at Harvard. Is that Ollie? Yeah. So you see, this is the level of students that he takes on, but also they go on to do these amazing things as well, and clearly retain that enthusiasm even when they're not in science. I often see George at the whiteboard or the blackboard discussing in real time his ideas and really inspiring and helping his students and postdocs along. And it's really fun to be in those group meetings. Okay? But in addition to all of this, George is also a very nice person. Okay? You can always rely on him for an interesting, lively chat and good advice, whether it's in the department or in the pub. And I should say that George is also a dab hand at the barbecue. He's also a husband, father to 2 young boys. He's overnighted at Legoland, something I'm very envious of. And he's also a big fan of cricket. And just to use a sporting analogy, George would be classed as a good all-rounder, somebody who can both bat, bowl, and field. However, in George's case, I don't think good is good enough, okay? George would be a great all-rounder, an absolute legend, and somebody who's supremely talented across the board and is invaluable in the team. So George, the group, the department, and the college, we're very lucky to have you, and we all look forward to seeing your achievements, and congratulations on your well-deserved professorship in theoretical physics.
Okay, now for something completely different. Well, maybe not completely different. Okay, so I've given myself a little bit of a large brief to talk about here in the abstract, but I will try to touch on these things. So basically, I've organized this talk to try and tell you what we've learned about neutrino physics in the last few decades that span my career, so going from undergrad to PhD to postdoc to academic and where I am today. So the thing I want to stress, first of all, is that all of the research I do is in big collaborations. It's all big groups of international physicists. So everything I'm presenting is not just me. And there's a huge amount of people to thank, and many of them don't like having their photos taken, so they're not all in these slides. So let's start at the very beginning. What are neutrinos? They are weakly interacting, chargeless, fundamental particles with virtually no mass at all. They're negligible. In fact, they do very, very little at all. They're probably the most useless of all the particles we know of. But in my mind, the most interesting because of it. So we know they exist because of beta decay. So beta decay is when you have an unstable nucleus. So this parent loses an electron, a beta particle, to become more stable. So it becomes a more stable daughter. And when this was first discovered at the turn of the 20th century, they measured lots of beta decays of the same isotope, and every time they measured a different energy of this electron. But if you're splitting energy between just two particles, there should be only way you can do it without breaking the conservation of energy and momentum. So something was going wrong here. This was a big no-no for physics. And the solution was proposed by Pauli, who saw that as well as the electron being produced, there must be another particle that was being produced in these decays and taking away some of the energy, a different fraction each time. Only that particle, its key characteristic, is that it's never detected. So this is what I learned as an undergraduate when I was at the University of Sheffield. I did find one photo. That's me, and that's my husband. So we both like hiding in the back photos. And I found neutrinos pretty exciting because, I guess, because of the challenge, maybe. Where do neutrinos come from? So there's lots of sources of neutrinos. Anything that has beta radioactivity in it will produce neutrinos, including the humble banana. Rock. There's a lot of radioactivity in the Earth, in the rock around us, uranium and thorium. That produces neutrinos. Nuclear reactors produce neutrinos in their fission reactions. The sun is a huge nuclear reactor. There's a huge amount of neutrinos produced in the nuclear reactions in the core of the sun. Cosmic rays are high-energy particles raining down on the Earth from outer space. And when they interact in the atmosphere, they produce various exotic particles, including neutrinos. And then the supernova. A supernova is a massive explosion at the end of the lifetime of a star, and this produces a humongous amount of neutrinos. And finally, and we'll come back to this later, we can produce our own neutrinos, making beams using accelerators. So that's where they come from. How do we actually go about detecting them? And the answer is with great difficulty and very rarely. Neutrinos are incredibly weakly interacting. It's basically like seeing an invisible man in a crowd. A neutrino, it doesn't have any charge, it's got so little mass that it just goes through everything undetected. So the only chance of seeing it is if it bumps into something and gives that something a boost of energy, and then you can then see that particle. So in this case, if a neutrino bumps into an electron, that electron is moving at a high speed because of the energy it's been given. And in water, if a charged particle is moving at enough speed, it will produce a flash of light called Cherenkov light. And if you put a lot of detectors in the way of that flash of light, you will see a beautiful signal, which is a ring of light. So this on the right is the Super Kamiokande detector, and each of these little blobs here is a very sensitive light detector called a photomultiplier tube. They're actually 50 centimeters in diameter, so these are big. This is a huge detector. And I would say that this picture is probably the picture that got me into my career, because I saw this as an undergraduate, and I thought this was the most beautiful detector in the world. So the other thing about this detector is it has to be deep underground. Why? Because of those cosmic rays I told you about. They're raining down on the atmosphere, and they're producing, as well as neutrinos, a whole load of charged particles that we would detect much more easily in our detector if it was here on the surface than the neutrinos. So we have to go away from all of the known sources of radiation, and we go deep underground. Whoops. Now, holes underground are quite expensive. It's not easy to make a big hole under the ground. And when you have done, there's a lot of challenges. First of all, they're made of rock and dust. And mine dust is full of radioactivity because this is very dirty. So, you know, if I put my detector just in the mine, I'd never see anything apart from mine dust. You have to build a clean room underground. And if you're building a clean room, then you need to build showers so that anybody comes through the mine into your lab is nice and clean when they start work. And obviously, you can't just pop out for lunch and grab a sandwich from Greg's. You need to have a lunchroom underground. And of course, you have to solve the plumbing issue. 2 kilometers underground, there aren't any sewers. So if you want to have any home comforts, you've got to build them yourself. So I was thinking about doing a PhD, and this was sort of the big story at the time, the solar neutrino problem. We know that the sun produces neutrinos. We know how energetic the sun is, and we know how much energy each fusion interaction produces and how many neutrinos. So we should be able to calculate how many neutrinos we can see from the sun. And that's what this guy, John Bacall, did. And these central columns in this graph, so this is a plot from the time, and I realized that maybe the resolution doesn't stand the test of time very well. So the central columns here are the predictions, and then on the outside are the measurements of experiments. So there's various experiments that were trying to measure solar neutrinos. There was the Davis experiment in South Dakota that was using chlorine as a target, and that measured for something like 30 years. They kept measuring 1/3 as many neutrinos as expected. And I really admired the determination of this. People say, oh, your results must be wrong. It's like, no, they're right. The theory is wrong. The Super K experiment, that was also measuring solar neutrinos and measuring about half as many as expected. There was another experiment with gallium, but I don't have any pretty pictures of that. So the thing about all these experiments is that they are looking for electron neutrinos. So there's actually 3 different kinds of neutrinos, but normal matter is made of neutrons and protons and electrons. So since the sun is made from normal matter, we expect it to produce electron neutrinos. But there was a theory that maybe you could explain this deficit if these electron neutrinos were changing to other types of neutrino, or other flavors, as we call it, as they were traveling from the sun to the Earth. So that was why the Sudbury Neutrino Observatory, or the SNO experiment, was built. So this was designed to measure all neutrino types. And I saw that there was a PhD on offer at the University of Oxford, and I also knew that SNO was in Canada, and I quite wanted to visit there. So I was very lucky to get this position, and I turned up as a fresh-faced graduate student and finally got to go out to Canada, to Sudbury, which I found the world's 2nd tallest freestanding chimney, a lot of large pocket change, and the world's deepest nickel mine. So I learned that Sudbury is not perhaps the most beautiful corner of Canada, but over the years I've become to be rather fond of the place. It's also the home to the world's deepest flushing toilets. And, of course, the SNO experiment, which is another absolutely beautiful neutrino detector. And I met a huge amount of very talented physicists who were working on this experiment. Again, the resolution is so bad that I can't quite tell if I'm in this picture. And I don't think you are in it either, Steve, as well as I can say. But okay, so SNO, the experiment, was designed to measure all types of neutrino. So it's basically a 12-meter wide acrylic vessel filled with heavy water. And then a lot of these photomultiplier tubes to look at that and measure the light. And the heavy water is special because there's 2 kinds of interactions, one that's only sensitive to the electron-type neutrinos, and another that's sensitive to all of the types of neutrinos. And the results, so I joined this experiment just after they started taking data. I felt like the classic physics goal hanger. I let them do all the hard work and solve all the problems, and then I turned up and I got to do the analysis, which was pretty fortunate. So the results, which I contributed slightly to my first year of my PhD, is that the electron neutrino measurement was still in deficit. It was very much about 1/3 as much as we expected. But when we measured the neutral current, which was sensitive to all of the neutrino types at once, it was in agreement with the theory. So this was pretty strong evidence that neutrinos are changing type on their way from the sun to the Earth. Such strong evidence, I guess, that Art McDonald, the director of the SNO experiment, won the Nobel Prize for it in 2015. And my small contribution was that I was actually measuring the spectrum of these electron-type neutrinos. So we know that the way they change is actually energy dependent. And you can measure the energy of the interaction and extract this spectrum. So why is this happening? This is explained by neutrino oscillations. So basically, the neutrino types that we measure, the electron type, the muon type, and the tau type, are made up of a mixture of different mass states. So we imaginatively name them 1, 2, and 3. And these mass states, if you think about them as waves, they have different mass or different energy, and therefore they travel at different speeds, or they have different wavelengths. So depending on where you are in time and space, when you add them up, sometimes they add up constructively, and sometimes they add it destructively. And this governs what type of neutrino you are seeing. You can write the probability in terms of the distance the neutrinos travel and their energy. But the important thing, the main message you can take from this to start with, is that if it's made up of mass states and there's a difference in mass, then neutrinos must have mass. They're not massless particles, which we thought they might be for a time. So the obvious question is, how much do they weigh? So after my PhD, I became interested in this process called double beta decay. So I showed you beta decay before. Double beta decay, it's the same thing, except two of them happen at once inside the same nucleus. So you have two neutrons decaying to two protons, two electrons, and two neutrinos. So you've still got neutrinos carrying away some of the energy which would otherwise go to the beta particles. So you still measure a continuous energy spectrum if you measure the energy of all the electrons given out. But, and some of you might notice this, I've been calling them neutrinos, but actually they've got this little line over the top which makes them antineutrinos. So every particle has an antiparticle. And normally the antiparticle has the opposite properties. So the electron is a negatively charged particle. The antiparticle of the electron is the positron, which has positive charge. But the thing is, neutrinos are so, I don't know, they don't have a lot about them. So what makes the difference between a neutrino and an antineutrino? They don't have charge. So how can you tell whether it's a neutrino or an antineutrino? Maybe they're the same thing, or they can act as the same thing. In which case, there's this exciting probability of this new process called neutrino-less double beta decay. So in this case, your two neutrons still decay to two protons, emitting two electrons, but the neutrino never leaves the nucleus. It just sort of facilitates the decay here, which means that it's not carrying away any of the energy. So all of the energy of the decay goes to these two electrons. So instead of measuring a continuous energy spectrum, you would see a very fixed energy given to the electrons. So the goal is to search for this specific process of two electrons with exactly the energy of the decay of the candidate isotope. So there's only a few isotopes that can do this, so you have to pick carefully. And this process still happens. And the challenge is really like searching for a needle in a haystack, this. This is such a rare process. The half-lives are so much longer than the age of the universe that you need a lot of isotopes, and you need to measure for a very long time, and you need to move anything that might be a background to this process from your detector. But the good thing is, if you did see this, you know something about the neutrinos, the way it acts as an antiparticle, and also the rate at which this happens is proportional to the mass of the neutrino. So the heavier it is, the more likely you are to see this process. So I went off to do my first postdoc at the University of Sussex on the COBRA experiment, working with Kazuba and the rest of the COBRA collaboration. So this experiment was based under a mountain in Italy in the Gran Sasso laboratory. And we were just building a prototype. We were trying to prove that you could build this kind of detector and make the backgrounds low enough that this measurement was feasible. So it was a lot of fun for 3 years. I mean, spoiler alert, we didn't detect neutrino-less double beta decay. Nobody has yet. But I went on after that. I did another postdoc on the Snow Plus experiment back at the University of Oxford. So actually, George, you will see that my map isn't very impressive either. It's all in the UK. apart from an occasional trip to Canada. So you might recognize a strong similarity here between the SNOW experiment and the SNOW Plus experiment, because really, we just retrofitted the SNOW experiment. It's the same detector. The heavy water was given back to Atomic Energy Canada, and we've been working to fill the detector with a liquid scintillator, which is actually much better at detecting lower energy interactions because it gives out a lot more light. So there's a whole amount of challenges of retrofitting a detector that's based 2 kilometers underground at the bottom of a mine. I don't think I ever used the spanner for any real purpose apart from photos. But, so I started working on this experiment in my postdoc, and I'm still working on it now. And spoiler alert, we still haven't measured neutrinoless double beta decay, but we're working on it. So in the meantime, there's other physics you can do with neutrinos as well. So I'll spend the rest of the talk talking about the oscillations. So I showed this formula before, which is the probability that a neutrino that starts as one type might change to another type. And I said it was dependent on the distance the neutrino travels, L, and its energy, E. But it's also dependent on these properties, which sort of describe the actual oscillation. So this is how much of each mass state makes up the different parts to start with. And this is the difference in mass between these mass states. And if we really want to understand the oscillations, we need to measure these parameters. So you can use all sorts of different neutrinos to measure different oscillation phenomena. So we were looking at solar neutrinos, but people have also measured oscillations of atmospheric neutrinos. And there are experiments that have measured nuclear reactor neutrinos as well and shown that they oscillate. But if you really want to make precision measurements, the best thing you can do is control, the distance and the energy of the neutrinos to start with. So if you can make your own beams of neutrinos, then you can really tune these measurements. So when I got my first lectureship position at Queen Mary on the other side of London, I got the opportunity to join the T2K experiment. So this is exactly what T2K does. And again, I joined the T2K experiment just after it had started taking data. More physics goal hanging. So they built a neutrino beam at the J Park Accelerator Facility on the east coast of Japan. And you can focus the charged particles to make sure your neutrino beam travels in a particular direction. We measured the neutrino beam first to make sure we know what it's made of. And then you fire it all the way across Japan, 300 kilometers, to the far detector, which is Super Kamiokande, the same beautiful detector I've shown you before. The interesting thing is, I was very excited to work on Super K, but actually all my work was on the near detector, so I still don't work on this beautiful far detector. But you can ask questions. So actually, this beam of neutrinos is not electron neutrinos now. This is muon neutrinos. So if you start with the muon neutrino beam, you can ask the question, whoops, spoiler, do electron neutrinos beam when they've traveled across this large distance across Japan? And the answer is yes, they do. These are the first results from the T2K experiment. And you can clearly see that the electron neutrinos appear. And the more accurately you can measure it, as we have done over the years, then the more precisely you can measure these oscillations. But the really interesting question you can ask is, does the same thing happen for antineutrinos? And to explain why that's interesting, we need to take a little step back in time to the Big Bang. So in the beginning of everything, the Big Bang happened, there was just energy, right? Huge amount of energy from the Big Bang. But energy, we know, is equal to mc squared, mass times the speed of light squared. This is Einstein's famous equation. And you can produce matter and equal amounts of antimatter at the same time from energy. But the trouble is, it's got to be equal amounts of matter and antimatter. And when matter and antimatter come back together again, when they collide, they annihilate and you get energy again. So if this keeps happening, energy to matter, matter to energy, why are we here? What happened that means that we now live in a matter-dominated world? There isn't antimatter out there. You're not going to walk into anti-U tomorrow and annihilate, luckily. So, it's a big question. Why do we live in a matter-dominated universe? So there must have been some process in the past that favored matter over antimatter. And this has been a big challenge in particle physics. There's a lot of other experiments and accelerators that are looking to answer this, looking for this source of matter. We call it CP violation, but something that happens differently for matter and antimatter. And one of the hardest places to look, maybe why it's one of the last places to look, is neutrino oscillations. It's so difficult to measure the neutrinos in the first place. So you can compare the oscillations for neutrinos and antineutrinos and see if there is a difference. So the TTK experiment produced this paper in 2020, which we were very pleased with. It shows an indication of matter-antimatter asymmetry. So the data seem to prefer that the two processes are different, but we're still statistics and uncertainty limited. Really, we need to measure more precisely to confirm this. And the trouble is, you need a lot of neutrinos. You need a lot of interactions to measure this. So in the world of neutrino physics, quite often, bigger is better. And this motivates building the next generation of experiment. So the T2K experiment is firing neutrinos at the super K experiment at the moment. But we want to, well, firstly, we want to upgrade the beam, so we've got more neutrinos to start with, and we want to build a much bigger far detector, which is called hyper K. So this is going to be 8 times bigger than super K. It's still going to be under a mountain in Japan, but under a different mountain, because this one's already taken. So to give you an idea of just how big hyper-K is, this is the cavity. So we recently, and when I say we, I mean our Japanese colleagues, have finished excavating this colossal cavern. And I was trying to work out how big it is to give you an idea of scale. Even with the people there, it's hard to gauge. But I reckon you could park about 100 London buses in the floor of this cavity. Or to give you another sense of scale, it will take us 100 Olympic-sized swimming pools full of water to fill this up. It will be full of water eventually. We're not ready to do that yet, but it will take 6 months to fill this whole cavity up. This was when we just excavated the top of the cavern. That's the Hyper-K collaboration when we visited it a couple of years ago. So to give you another idea of the scale, you might have seen London Bridge on your way here. So Hyper-K is going to be 71 meters tall and 68 meters in diameter, which means it looks like this in comparison to London Bridge. It really is quite a big detector. It's a huge engineering project. My particular part of it is the outer shell, so to speak, this little bit on the edge here. The reason why this bit is important is because even though this detector is going to be under a mountain, some of those high-energy particles are still going to get underground. And because the detector is so big, we actually expect to have around 4 million muons a day passing through this detector. And that's much more than the number of neutrinos we hope to see. So if we can't veto these muons, we can't do any of the physics because we can't tell what's our signal and what's the background. The good thing is that the muons, because they're coming in from outside, they're going to be leaving flashes of light as soon as they enter the detector. So by having this little veto region on the outside, we can see if light appears here before the muon goes through. Whereas if a neutrino comes in, it won't produce any light until it interacts inside the detector. So in order to detect the light in this outer bit of the detector, we are going to install 3,600 photosensing units. They look like this. And we are going to make sure we collect and bounce all the light into those detectors using very reflective coating on all of the walls, on the inside and the outside. And we use something that's called Tyvek. It's very, very white, and we need about 6 football pitches worth of this material. So basically, what I'm working on now is a glorified wallpapering project. But it's not simple wallpapering. It's got to happen in this space, which is 1 meter wide, 200 meters in diameter, and 71 meters tall, under a mountain in Japan, don't forget. And also, we need to make sure that we keep this as a clean, radioactively pure detector environment. So we really need to do this in a very scientific way. But this is what is keeping me awake at night at the moment. So why is it worth it? Well, apart from explaining our existence, if we can find this matter-antimatter asymmetry explanation, what else can the neutrinos do for us? So these large underground neutrino detectors, we can use them as the microscopes to really measure the neutrinos and understand the properties of the neutrinos. But we can also then use them as telescopes to observe distant astronomical objects. We've already got quite good at looking at the sun, but looking for supernovae or other astronomical phenomena that might produce neutrinos as well. So really, I think neutrino physics is going to move from understanding the neutrinos to understanding the sources that produce them, which is, it's an exciting prospect for the field, I think. So that's the story, that's where we are now, and as I said, this is all done in big collaborations. The great thing about being a neutrino physicist is you get to work with a lot of people from a lot of different countries. I get to go to Canada and Japan, but mostly I've worked in the UK, and there's a huge amount of people to say thank you to, so I need to do it globally. And thank you everybody for coming as well.
Hi, everyone. So Jeanne was my first PhD student working on the snow experiment. And I was impressed by the fact that before she actually even applied to the department, she came to talk to the group, which is that time was me and Nick Jelly. And she said she had read up about this, and this is the project she wanted to do. And if we didn't give her a place, she'd leave academia and go get a real job. So we didn't want that to happen. It took her on. And it seemed almost, straight away, it was sort of clear that Jeanne was the sort of student that you could throw into almost any situation, and she would figure it out. She was very focused, but still had the ability to kind of step back and see the bigger picture, and that was pretty rare. And she was, highly effective at it, sort of all this stuff. Anyway, I mean, the road to effect. In fact, I should sort of say, I thought she was totally unflappable. You put her in, any situation, and she was perfectly calm all the time. Although there was a moment near the end of her PhD when she was struggling to sort of finish writing up, and under a lot of pressure to get her results into a paper, which became one of the main publications of snow, which went on to win the Nobel Prize, as she mentioned, that she was under so much stress that some of her hair started to fall out. So this is something I can sympathize with. And as I was saying, the road from there to a faculty position is not a straightforward one, and you never know where you're going to end up or if you're going to get a job until you get a job. And there was a in between during, on her journey through this path, as she sort of finished her PhD, her first postdoc position, and which sort of looking to hang on for a little bit longer, I found some money through a Leverhulme fellowship for her to come back and work with us at Oxford for a couple years. And she was torn at that time as to whether she should take it, because it meant commuting between Hitchin and Oxford, spending half a week in each sort of place. And she wasn't sure if she should do that or just sort of quit academia and get a real job. So you can see Jeanne's trajectory in academia has been a series of threats to leave, basically. And her husband, Martin, told her, I think quitting academia and getting a real job is probably the sensible thing to do, but it's probably not the time to be sensible. And I'm glad to say that she's not been sensible sort of since then. It's been fantastic continuing to work with Jeanne on sort of projects. And I often hold her up as a role model because she's highly effective, highly efficient. And although, as she sort of said, she's worked on projects with lots of people on them, her contributions stand out. At the same time, she's maintained a very good work-life balance. And I think that's really something to celebrate. So thanks, Jeanne.
So it just ends with a few thank yous from me. Before I go on to our professors, I just want to have a little special thank you to our events organizer, Kenji, who does amazing jobs in the faculty organising his event, because it's his last week before he moves to New Zealand. Is that right, Kenji? Australia, I was very close. So can we just put our hands together to thank some of the unseen work that goes on? Thanks, Kenji, and all the team who support these so well. So, but I do want a special thanks to our speakers tonight, our two new or newish professors. Jeanne and I were trying to work out when she did become a professor. It's either 2 or 3 years. I know George's last year. So it's quite a special thing in academia that being recognised and being promoted to a professor. And these inaugural lectures are a really nice opportunity to celebrate that. So professors are academic leaders in our institutions. These are the people who are setting agendas in their research fields. They're working at the frontiers. They're providing inspiration. They're being ambassadors. I love the fact they take risks and are not always sensible. This is something which we need in our professoriate. We urgently need it. You see where it's urgently needed across the world. We need people who can, speak about the importance of and the excitement of our disciplines and the importance of education. As well as in their research fields, and it's clear, I think, tonight how excited George and Jeanne are about their research, and quite rightly so. They also provide academic leadership within higher education more broadly. So they're providing leadership on what we do in education, be that undergraduates through to our postgraduate students and research students. So important, essential part of what we do as in higher education. And they also have a really important role in setting the culture, what those research groups are like, how students are supported, how they interact with their colleagues. And it's great to have such amazing colleagues giving their talks today, who I know are really highly regarded in the department and in the faculty. So thank you so much. A heartfelt thank from me as sort of chairing up the faculty. Thanks for King's. I know your department hugely values all you contribute. And thank you for sharing some of that this evening. So a final round of applause for Jeanne and George.